Now, there's a couple of people will throw around haptic and tactile and force feedback and use them interchangeably. Really, haptics is both tactile feedback and force feedback. Tactile feedback is more of a sensation. It can be vibration, texture, temperature. When your cell phone is on silent mode and starts buzzing in your pocket, that's a tactile sensation. It's not directional. When I push on this desk, I have an equal opposite force that is going to balance out the force that I'm pushing on this desk. If I don't, I have motion, right? So that's a directional force, and that's the technology that is actually pretty darn expensive. This is your typical linkage-based device. What this is, it's like a robot arm. To get an applied force at your end effector, you apply torque at the joints. It's a pretty cool, sexy solution, but what happens if you want to adapt this design and make it for a bigger workspace? Let's say, like what you see on the screen here, this is kind of wrist range of motion, and you have an applied user force. But now you want to make it arm range of motion. Well, the problem is, as soon as you make these links longer, you end up with a bigger lever effect, so you can put much more force on these joints. So just to get the same amount of force you had on the previous workspace, you now have bigger motors, your system has now become heavier, so you have to compensate for that mass, and it becomes much, much more expensive. So it doesn't take long before a linkage-based solution just is not practical to very large workspaces. So one of the things, well, first of all, here are just some examples of various haptic devices, everything from a gaming device from Novent, and then Sensible Technology, who's probably the most famous haptic device company. They make the Phantom and also the Omni, which I'll get to. But we took a different approach. It's actually relatively simple. The idea is to apply force with cables. So what you can do is if you want 3 degrees of force feedback, you need 4 cables. Really, all you have to do is take your degrees of force feedback that you want, add 1, and that's how many cables you need. But better yet, these are now vector forces. These are not moments applied at a joint, so you can really scale your solution using the same components. This was a technology that came out of the Tokyo Institute of Technology. I met Dr. Sihak Kim while I was at the University of Washington, and I convinced him to start me in a startup Mimic with me in the beginning. So these are just some examples. This is an example of a 3-degree force feedback device. Now we've added 3 more cables, so we're now up to, we can do rotational force feedback. Your workspace is becoming a little bit more constricted because you have more cables, but you can take it further. 8 cables will give you grip force feedback. And there's another thing you may have noticed. These cables are pretty transparent. So you can really put a 3D display behind them and project your 3D images into the space you're working with. It's not really that simple because if you focus on your hands instead of the screen, you don't see 3D, but there's some tricks to account for that. And best yet, very scalable. You can make these things the size of a shoebox, or you can really make them the size of the room. And I try to think of, you can see how this guy jumps as he shoots the ball. I just don't, I think this would be very difficult to do with a linkage-based system. So now I'm going to talk a little bit about tissue. And this is just a slide I like, just because I think it relates to the dangers of improper simulation training. What the sign says is, hikers and bikers, move to the side of the road when vehicles approach. Clearly not very good advice. So, and this is really what happens. Can you imagine if you train somebody with a surgery simulator and you're taking maybe it's a vessel or some tissue and you think it stretches about 10 times the length of what it really should, and you think you have lots of elasticity, and then you get into the real application, next thing you know, you rip a vessel. And you're like, well, that's not what the simulator did. That's not what they told me to do. Well, that's the danger you really run here if you don't have accurate modeling. And this is really what I think has been the big problem with a lot of the simulators out there. They've been more video games than they have been something based on reality, something based on material properties, something based on continuum mechanics. And everybody loves to make this comparison to flight simulation, but really the complexity of modeling the human body is so much more difficult than flight simulation. The fluid dynamics is pretty well known in flight simulations. It's very achievable. It's hard to say that even offline, if you, in most cases, you can very accurately represent soft tissue. And just to really kind of talk about my point here, the tissue is nonlinear, inhomogeneous, anisotropic, viscoelastic, often exhibits pre-exhibit. Basically, bunch of engineering terms to mean this is difficult. And if you look at my thigh tissue, and I compare it to any of yours, it's going to be very different. My thigh tissue is going to be a bit different than my bicep tissue. My bicep tissue is going to have different material properties in the morning than it is in the evening. And worse yet, as soon as I extract it out of the body to try to measure those material properties, they completely change. So even if you have a very good modeling method, there's still the challenge of extracting these material properties. So my approach for my PhD was I was going to apply finite element modeling, which is a technique where if you have a very simple geometry with known material properties, you can very accurately predict what's going to happen if you push on it. Well, you can build more complex geometries by building them up like Legos. The more elements you have, the better accuracy you have. Unfortunately, the computation time gets very high. This is a type of problem normally wasn't a real-time problem. This is something where you press go and you'd get one solution after taking a lunch break. But you can take this modeling method and you can apply these fancy texture maps on top. Texture map is basically a sticker that you apply, and as a result, you can get some pretty decent deformation. I'm not going to say it's perfect, but it's still better than a lot of the video game spring mass type models that a lot of people use. So, and by the way, this first application, if any of you guys are squeamish, this would be the time to get a cup of coffee. I was dealing with male anatomy. So our first effort was TURP simulation. So this is transurethral resection of the prostate. We partnered with Dr. Robert Sweet at the University of Washington. So we did a lot of instrumentation of the scope. We attached the end of it to a tension-based device. You add a skin on top of it, and next thing you know, you had a simulator. We were relatively, it was a decent simulator. And a matter of fact, it ended up getting licensed out of the University of Washington and going to Medi. Problem is they didn't believe they needed haptic device technology. So we were sort of cut out of the development. The product has since been discontinued, so it wasn't very successful. So our next product, we tried to do laparoscopic simulation. We partnered with another bigger simulation company who contracted us to do it because we knew we could create a haptic system for about the fifth the cost of the existing simulators out there. Problem was there's a time to market issue. I was very naive on how quickly we could accomplish. The engineers are always confident. You always think you can get stuff done quickly. Unfortunately, that's not necessarily the case. And in this case, while we did get a prototype, it was maybe a couple of weeks late compared to what we were contracted to do. Problem is they felt that time to market pressure. And they still went an off-the-shelf device that was about 5 times the cost because they felt their competitors were getting a leg up on them in laparoscopic simulation. So again, we had a failure. Then we decided we'd go for, okay, well, maybe we'll make some off-the-shelf haptic devices. So we did two. We did a one-handed system called the Mantis Workstation and another called the Mantis Duo. We thought, great, the haptic devices that are one-handed out there are about 13,000. We can make one for about 7,500. We thought we had a great app. As soon as we have our prototypes out there, Immersion comes out with the Omni, which is less than 2,000. So, they talked about the market changing. Boy, this was certainly the case. Now, Omni was smaller. It was made of plastic. It certainly wasn't as good as our system, but it was a lot cheaper, and that's really what universities are going to buy.